Welcome to the Deep Dive. Today we're tackling a really tricky technical spot in large language models. It's about making reinforcement learning with verifiable rewards, RLVR, stable and scalable. Because right now,
It often feels like it could just, well, fall over during training.
it's a major headache, especially for high-stakes LLM tuning. We've been looking at some source material that puts forward a pretty neat potential solution. It's called quantile advantage estimation, or QAE.
QAE.
And our mission today really is to unpack why this QAE approach seems to tame that instability we see in RLVR, particularly how it tackles this thing researchers are calling the entropy dilemma.
Right, the entropy dilemma. But maybe first, a super quick refresher on RLVR, just so we're all on the same page.
Good idea. So RLVR is about improving LLMs by rewarding them when their output, like a chain of reasoning, is demonstrably correct. Verifiable. Often it's just a simple reward, like a 1 for correct, 0 for incorrect.
Essential for things like math problems or generating code, where you need the answer to be right, not just plausible. Exactly. But like you said, training it is like walking a tightrope because of these policy entropy problems.
Okay, let's get into that tightrope walk.
Yeah.
Section 1, the dual perils of entropy in RLVR.
Right. So the core tension in RLVR fine-tuning is this balancing act. The model needs to maximize its reward, get more ones, but it also needs to maintain some randomness, some diversity in its policy entry.
Why the diversity?
If it becomes too single-minded, too rigid, it stops exploring. It might find an answer, but maybe not the best answer. But if it's too random, its learning signal gets washed out and it just thrashes around.
So the sources talk about two big dangers here, stemming from that tension. First up, maybe the more obvious one, entropy collapse.
Yeah, collapse is when the policy sharpens way too fast. The model just latches onto the first okay-ish strategy it finds.
Locks in too early.
Precisely. It suppresses exploration, performance hits a ceiling, a local maximum, and it just stops improving. It never reaches its full potential.
Okay, that makes sense. But the sources seem quite focused on the flip side, which feels a bit less intuitive. Entropy explosion.
Right. This often happens when you try too hard to prevent collapse. You push for more exploration, but it goes haywire. You get this uncontrolled surge in randomness.
The model forgets what it learned.
Sort of, yeah. It leads to what the researchers call signal-degrading divergence. The useful learning signals just get lost in the noise. It becomes super inefficient. Progress stalls completely. It's like trying to explore everything at once and learning nothing.
And there's actual data showing this isn't just theoretical, right? The source material mentions specific models.
They looked at Qwen3 8B base using standard RL methods like DPO, and sometimes they'd use techniques like ClipHire, specifically designed to encourage diversity and prevent collapse.
Okay, so what happened when they did that?
They basically traded one problem for another. The data showed this huge spike in entropy really early on, like between training steps 10 and 80.
A massive spike.
Yeah, high volatility right out of the gate, and it immediately causes issues.
So it doesn't just crash, but it limits things.
Exactly. That early instability seems to put a hard cap on how good the model can get. The sources noted that even though it avoids immediate collapse, the volatility sticks around, and performance pretty much flatlines after maybe step 100. It just stops getting better.
That's a crucial point then. It shows that stability isn't just about avoiding collapse. You can't just crank up the randomness dial.
No, effective RLVR needs the entropy to stay within a kind of productive zone. A stable channel, if you will. Enough exploration to find better solutions, but not so much that it destabilizes the whole learning process.
Okay, so we've established the problem. This entropy can either collapse or explode, and both are bad. Now, section 2. Why is this happening? Where does the instability actually come from, especially in methods like DAPO or GRPO that are supposed to be pretty solid?
Well, the research we looked at points the finger not at the fancy parts of the RL algorithms, but at something much more fundamental. The baseline used for advantage estimation.
The baseline. Explain that a bit.
So these value-free methods, like DAPO, they need a way to judge if a response was good or bad relative to what they expected. They typically use a simple empirical mean baseline. They look at all the rewards in a batch, average them out, and use that average as the benchmark.
Okay, an average. And we know averages can be sensitive, especially to outliers.
That's the core insight here. A few really high reward samples, those rare ones when most are Dearies, can drastically inflate that mean baseline.
Ah, I see where this is going. If the baseline gets artificially high.
Then perfectly decent responses, maybe ones that should be seen as okay or even good, suddenly look bad in comparison. They get classified as having negative advantage simply because they weren't as spectacular as the few outliers in that batch.
So the model gets penalized for things that aren't actually failures.
Right. It's improperly penalized.
Yeah.
And this constant incorrect negative feedback on competent but not stellar responses is what seems to drive that policy instability, that entropy explosion we saw earlier.
Does the data back that specific connection up?
It does. Observation 3 in the source material highlights this. It shows that the big entropy spikes and the instability early on are disproportionately driven by these samples flagged with negative advantage. The policy is changing erratically because it's being told, wrongly, that decent attempts are failures.
Okay, so that links the mean baseline to the explosion.
Yeah.
What about observation 2? That seemed interesting too, about token level controls.
Yeah, that tackles the attempts to fix this by tweaking things at the word level, like using clip hire and DPO to force more diverse token usage
Does that work?
temporarily. Initially, you do see more diverse anthropomorphic tokens, as they call them. Think internal reasoning markers, like the model saying, wait, or let's consider, or perhaps. It's just genuine exploration of different thought processes.
But you said temporarily.
Right, because after that initial burst of diversity, the token distribution tends to homogenize again. The model falls back into using very rigid, predictable reasoning templates. Lots of so, let, therefore.
And that shift back to rigidity.
Lines up almost perfectly with when the performance plateaus, around that step 100 mark we mentioned. It's a visible sign that the exploration boost was superficial and didn't last.
So the takeaway from the researchers was, don't fiddle with the tokens.
Pretty much. Trying to tune token level things, like the clipping threshold, is just papering over the cracks. The real issue is more fundamental. It's the design of the response level baseline. The mean is just too easily skewed.
Which brings us neatly to section 3, the QAE solution. If the mean baseline is the villain, how does quantile advantage estimation fix it? What is a K-quantile baseline?
Okay, so QAE swaps out that simple mean for a group-wise K-quantile. Think of a quantile like a percentile, but expressed as a fraction K between 0 and 1. Instead of asking what's the average reward, it asks something like, what reward level did the top say 60% if K 0.6 of response is achieved?
And why is that better?
Quantiles are inherently robust to outliers. One amazing success won't dramatically shift the K-quantile baseline the way it shifts the mean. It provides a much more stable reference point.
And for the simple binary rewards in RLVR, 0 or 1, this QAE baseline simplifies quite elegantly, right,
Yeah.
into a kind of switch.
Exactly. The sources call it a two-regime gate mechanism. It boils down to comparing the chosen quantile parameter, K, with the actual success rate for a given query. Let's call it PQ.
So how does the switch work based on K and PQ?
The QAE baseline, let's call it BK, becomes either 0 or 1. It's set to 0 if the success rate PQ is less than or equal to 1 minus K. And it's set to 1 if the success rate PQ is greater than 1 minus K.
Okay, let's break that down. Regime 1, hard queries. This is when the success rate PQ is low, below that 1K threshold. So the baseline BK is 0. What happens then?
This regime becomes purely focused on exploitation. Since the baseline is 0, only successful responses, reward R1, get a positive advantage signal. They're the only things reinforced. Incorrect responses, R0, get 0 advantage. They're essentially ignored for updates.
So for hard problems, the model just learns from its wins, however rare they are.
It doesn't get confused by being penalized for failures it doesn't yet know how to avoid. Very targeted.
Okay, now, regime 2, easy queries. Success rate PQ is high, above the 1K threshold. Now the baseline BK flips to 1.
And this flips the learning focus to exploration or maybe refinement. Now, a correct response, R1, gets 0 advantage because the baseline is 1. The model isn't wasting updates reinforcing things it already does well.
So what does get updated?
The focus shifts entirely to the failures, R0. These now get a negative advantage. So for easy problems, the model is pushed to eliminate those remaining errors, to refine its policy, maybe find more robust ways to succeed.
That's quite a clever switch. And it leads to something the sources really emphasize, sparse updates.
Yes, this is a striking consequence. With a reasonably tuned K, they suggest K 0.4 works well as a default. It turns out that roughly 80% of all the responses generated during training end up getting 0 advantage.
80% get ignored for updates.
Correct, either because there were failures on hard queries, regime 1, or successes on easy queries, regime 2. The learning effort gets concentrated entirely on that crucial 20%, the rare successes on hard problems and the residual failures on easy ones.
They call this the response level 80-20 rule.
Yeah, and it strongly suggests that standard mean baseline methods are incredibly inefficient, wasting compute cycles updating based on noisy or uninformative samples. QAE acts like a filter, focusing only on the samples that actually drive meaningful policy improvement.
Okay, this QAE approach sounds efficient, but does it actually solve the stability problem? Does it prevent the explosion and collapse? Let's move to section 4, two-sided entropy safety and performance gains.
It seems to. The researchers provide a theoretical argument for this. They show that QAE, under common first-order softmax updates, offers a kind of built-in two-sided entropy safety guarantee. It naturally resists both extremes.
How do the two regimes contribute to that safety?
Let's trace it. In regime 1, the low success, hard queries where the baseline is 0 QAE acts to minimize the entropy increment. Because it's only reinforcing successes, it discourages random exploration. It's inherently resistant to entropy explosion.
Okay, explosion-proof in hard cases. What about collapse in easy cases?
That's where regime 2 comes in. High success, baseline is 1. Here, QAE maximizes the entropy increment. By penalizing failures and ignoring successes, it forces the policy to diversify, to seek out variations, actively pushing back against collapsing into a single rigid solution.
Collapse-proof in easy cases. That's neat. And this is fundamentally different from just tweaking tokens.
Yes, because token-level controls just adjust the size of the update step. They don't change the core decision of whether a response gets a positive or negative advantage signal in the first place. QAE changes that fundamental calculation via the baseline.
All right, theory sounds good. What about the results? Did it actually work in practice?
The empirical results look pretty compelling. Table 2 in the source material shows QAE, implemented basically as a one-line code swap for the baseline calculation, leads to much more stable policy entropy compared to the volatile mean baseline methods.
Stable entropy is good, but did performance actually improve?
Yes, and consistently. They saw sustained gains in pass at 1 accuracy, which measures that verifiable correctness. It worked well on both the 8B and the larger 30B Qwen3 models they tested, and it seemed compatible, even synergistic, with other methods like ClipHire.
Can you give us a specific number? How much better did it get?
Sure. On the Qwen3 8B base model, just adding QAE on top of the existing ClipHire method boosted the AM24 pass at 1 score, that's a math reasoning benchmark, by a relative 21.5%.
Wow, 21.5% is a significant jump.
It is. It took the score from around 39.7% up to 48.2%. That's a substantial improvement in reliable reasoning capability, achieved just by changing how the baseline is calculated.
And did this improved accuracy come with better reasoning or just finding tricks?
The sources suggest it's genuine improvement. They observed that QAE led to a co-growth of those internal AHA reasoning markers, those diverse thought process tokens, alongside the external accuracy gains. So it seems QAE helps turn that stabilized exploration into more productive, reliable reasoning, avoiding the noise trap.
It avoids that spike then plateau pattern we saw with the mean baseline.
Exactly. It keeps the model learning effectively within that productive entropy range.
Okay, let's wrap this up in the outro. Stepping back, what's the big picture takeaway from this deep dive into QAE?
I think the central finding is really about reframing how we think about RLVR stability. It suggests the core problem isn't about endlessly tweaking token-level hyperparameters like clipping thresholds.
Which feels like a constant battle.
Right. Instead, it frames it as a fundamental issue in baseline design. Moving from the simple, noise-sensitive empirical mean to the statistically robust K-quantile baseline seems to address the root cause of the instability.
And the mechanism behind it is this dynamic two-regime system governed by the K-quantile. It intelligently decides whether to focus on exploiting rare successes or exploring ways to eliminate residual failures.
Yeah, it stops treating all samples equally and uses that K-threshold to figure out the difficulty level and prioritize updates far more effectively. It manages the exploration-exploitation trade-off automatically based on the current policy's performance.
And maybe the final thought to leave listeners with, circling back to that striking 80-20 rule.
Yes. The observation that QAE achieves stability and efficiency while only updating about 20% of samples is really provocative. It suggests that maybe the biggest bottleneck in scaling up RLVR isn't about finding ways to deliver bigger or faster
Oh,
updates,
rather.
but rather about intelligent selection. It's about figuring out which small fraction of experiences actually contains the information needed to improve the policy. The challenge might be more about prioritization and filtering noise than just brute force computation. Deciding who learns might be more critical than how much they learn from each example.